We will continue discussing the words and disambiguation methods, and today's focus will be on discussing overlap based method in more detail and also start the supervised method. So, as we have seen before, words and disambiguation is the problem of obtaining the sense of a set of target words or of all words, which is called all word WSD. This is a more difficult problem against a sense repository like the wordnet or a thesaurus, not same as wordnet, does not have the semantic relations. Okay, thesaurus does not have semantic relations, using the context in which the word appears. Okay. So, the key point is to obtain the sense of the word or words against a sense repository using the context. Okay. So, the example which is running is the example of the word operation, which can have a computer science sense or military operation sense or medical operation sense or mathematical operation sense. So, the goal would be to find out the sense of the word as dictated by the context. Now, we have been discussing the knowledge based methods, machine learning based methods will be covered after this, and then hybrid approaches. In the knowledge based approach, we rely on knowledge resources like the wordnet, thesaurus, etc. We may use the grammatical rule for disambiguation. We may also use hand coded rules for disambiguation. Then in the machine learning based approach, we need a sense smart corpora from which we have to produce the correct sense. In hybrid approach, both corpus and semantic relations are considered. So, knowledge based approach was covered, and overlap based approach is one kind of such approach. Now, in overlap based approach, as the slide shows, we require a machine readable dictionary. We find the overlap between the features of different senses of ambiguous word, the sense bag, and the features of the words in the context. We call it the context bag. These features could be sense definitions, example sentences, hypernyms, etc., and the features could also be given weights. The sense which has the maximum overlap is selected as the contextually appropriate sense. Now, an example was discussed last time. We are repeating this now. The sentence which is given is, on burning coal we get ash. Okay. So, here the word to be disambiguated it is ash. This is shown in red. The contextual clues are the word burn and coal. Now, sense bag contains the words in the definition of a candidate sense of the ambiguous word, and the context bag contains the words in the definition of each sense of each context word. So, here we are going to disambiguate ash. So, from the word net we find that the noun ash has three senses. The first sense is the most commonly known sense of ash, the residue that remains when something is burnt. Okay. So, this is the first sense. Second sense is that of ash tree, and third sense is that of elastic wood. So, we have to find out from the context which sense applies in this particular case. The first sense is the residue sense obtained after burning, second sense is the tree sense, third sense is the wood sense. So, when we read the sentence once again, on burning coal we get ash, we find that it is the first sense which is applicable. Now, from the context we find that burn and coal and get are the content words in the environment, and in the sense bag for each sense we take the gloss, which is the definition of the sense, and the example sentence, and find out if the context bag has overlap with any of them and which one has the highest overlap. So, if you look at the first sense of ash, the gloss is written as the residue that remains when something is burnt. So, the context words which are burn, coal and get have found an overlap in the definition. Okay. The first sense has the overlap in the form of burn. No other definition, as you can see here, has an overlap So, we declare the first sense as the winner, and we will be correct here. So, the first sense is the winner, and this is the sense in which the word ash is used. So, this was discussed, and we have seen that the main critique is that proper nouns are often strong indicators of the sense, and they are not used in this method of disambiguation. So, the other point is that there can be severe topic drift because of wrong overlap. All right. Then we made use of then we studied the extended Lec algorithm, where the overlap is found not only from the word's own synset and the gloss and example sentence, but also from the related semantically related nodes. So, one would like to see the overlap from hypernymy, hyponymy, meronymy, holonymy, and so on. Wherever there is a connected node, we would like to go into that node, obtain the words in that node, create the sense bag, and then find out the overlap. So, this is extended Lec algorithm, and here the main problem is that the clue words which come from the related nodes can again cause topic drift and mislead the algorithm to believe that this is the sense. So, an example was shown in extended Lec. On combustion of coal, we get ash. So, in its own node, there is no overlap because we do not have the word burning here, even though it is synonymous. But we do get an overlap when we follow the hyponymy semantic relation. So, the residue that remains when something is burned, and fly ash is a kind of ash where we find that the definition is fine solid particles of ash that are carried into the air when fuel is combusted. So, combusted has an overlap with combustion. So, this is the winner sense. So, these things were discussed, and the critique is that there can be topic drift. Now, we move on to another algorithm which is known as the Walker's algorithm, and we discuss it in detail. So, it is important to understand that Walker's algorithm and the subsequent algorithm, which is conceptual density based algorithm, yet another algorithm which is page rank based algorithm. These are different interesting ideas, algorithmic ideas, which are applied to weight the sense. Okay. So, these are mainly weighting mechanisms or scoring mechanisms to bring to the fore the importance of a particular sense for the purpose of disambiguation. But it is important to understand that fundamentally, okay, at the basic level, these are nothing but overlap based algorithm. They essentially measure the overlap, but give a principled way of scoring a particular sense. So, let us go ahead with the Walker's algorithm. This is a thesaurus based approach. Okay. So, this is not really based on WordNet. WordNet may assist this algorithm, which is an interesting idea, but it is based on the thesaurus. The first step is that for each sense of the target word, find the thesaurus category to which that sense belongs, and step 2 is calculate the score for each sense by using the context words. A context word will add 1 to the score of the sense if the thesaurus category of the word matches that of the sense. For example, let us take the sentence, the money in the bank fetches an interest of 8% per annum. The target word here is bank, which we know has two senses, one is the river bank sense, the other is the financial bank sense. Now, what does the common sense tell us? We see that in this sentence there are many words which relate to financial domain. Money, for example, is the first word which does that. Fetches and interest. Interest is again an ambiguous word, and one of its senses is in the financial domain. 8% per annum. So, per annum is also a fixed phrase which is highly used in the financial domain. 8% is the rate of interest. So, the clue words here are money, interest, annum and fetch. Fetch is also of course an important clue, because this is a verb, a content word in the context. So, here is how the algorithm goes. We open as many counters as there are for the senses of the target word. Now, let us assume here that the bank has the noun bank has only two senses, that of the finance sense and the location sense. So, what is happening here is that the moment we see money, okay, we add the count of finance counter by 1, we increment the finance counter by 1, and money has no sense of location. So, nothing gets added to sense 2. Interest similarly has many senses, but one of the senses is in the financial domain, that increments the count by yet one more 1. Nothing gets added to location sense. Fetch does nothing to either sense. Annum is a financial term, and so this adds 1 again to the finance counter, nothing gets added to location. So, after we have made use of all the annum also does the same thing. After we have made use of all the clues, we find that the finance counter value has become 3, location counter value is 0. Okay, so, this is an elegant simple idea which says that for each sense go on incrementing the counter from the overlap of the context word and thereby find out the winner. So, the problem here though is that though the algorithm is elegant, the problem is who will say that money, fetch, annum, they have finance domain sense. Okay, how do we know that? Is there a data structure or a knowledge base which will facilitate that? The answer to this question is yes. There is something called an ontology which is independent of language and which is purely devoted to organizing the meaning nuggets in a situation into a hierarchy. Okay. So, this ontology is the ontology of let us say financial domain, and the ontological nodes which are the properties of different senses, the general properties of different senses, they will denote that annum, money, interest, fetch, they are financially relevant words, they belong to the domain of finance. Okay. And we have to make use of that ontological structure. The thesaurus itself mentions in the senses of the words the ontological information. So, from this information it is possible to get the clues of the words in terms of their domain dependence, and we can go on incrementing the counter as described in the algorithm. So, this is the main idea of the Walker's algorithm. Okay. So, we look at the slide here and see that the finance sense has counter value incremented to 3, location counter is 0. We move on to the next algorithm, which is the conceptual density based algorithm proposed by Agirre and Rigau back in 1996. This algorithm again has a few interesting ideas, and the main idea is that we have to select a sense based on the relatedness of that word sense to the context. So, this is the fundamental idea, and relatedness, how was it measured? It was measured in overlap based approach in terms of the overlap between the sense bag and the context bag. Now, in case of conceptual distance or density, the relatedness is measured in terms of the conceptual distance. That is, how close is the concept represented by the word and the concept represented by its context words are. The approach uses a structured hierarchical semantic net, in this case it is the word net, for finding the conceptual distance. Smaller the conceptual distance, higher will be the conceptual density. That is, if all the words in the context are strong indicators of a particular concept, then that concept will have a higher density. So, we will illustrate this by means of an example. We will come to this particular slide after some time. We have taken here an example sentence, which is, the jury praised the administration and the operation of Atlanta Police Department. This example is from the paper by Agirre and Rigau. Okay. So, here we would like to go back to the wish list. The wish list is that the conceptual distance between two words should be proportional to the length of the path between the two words in the hierarchical tree, and here the tree is word net. The conceptual distance between the two words should be proportional to the depth of the concept in the hierarchy. So, if the two nodes are high up in the hierarchy, then their conceptual distance also should be more. So, because of these considerations, we come up with a scoring mechanism, which is for the conceptual distance of a concept with respect to m senses in the context of the word. So, this is the formula. The formula is CD C comma m is equal to sigma I equal to 0 m equal to 0, sorry, I equal to 0 to m minus 1, and n hype to the power I to the power 0.2.0 divided by descendants of C. C is the concept, n hype is the mean number of hyponyms, h is the height of the sub hierarchy, m is the number of senses of the word and senses of context words contained in the sub hierarchy, CD is the conceptual distance, and 0.2 is the smoothing factor. So, this formula is used for finding the correct sense with respect to conceptual density. That means, higher the score of a particular concept, more is the chance that this will emerge as the winner sense. So, here is an example of the situation involved. Entity is the root of everything, and under that there are various subtrees. You can see here in the financial domain, this bank 1 is the first sense of bank. In the financial domain, there is this word money also. Then the second sense of bank is the river bank sense, which comes under location, and it is shown here. The conceptual density based Watson disambiguation algorithm works as follows. The dots in the figure represent the senses of the word to be disambiguated, or the senses of the words in the context. Okay. So, first what is done is that the senses of all the words, both target and non-target, are collected. This happens by means of a window around the target word. Okay. Now, we collect the words, we build the subtrees from the word net hierarchy, and whichever subtree has the maximum conceptual density as per the formula given before becomes the winner sense. Okay. So, those are the senses which will be picked up from the window as the winner senses. So, this is an all word sense disambiguation algorithm. So, the disambiguation happens for all the words for all possible senses, and what we do is that we note the number of nodes in a particular subtree but we also give weightage to how high the concept is in the conceptual hierarchy, and we also give weightage to the number of descendants and so on. So, based on this we finally obtain the correct sense of the word. So, here is an example. The sentence is, the jury praised the administration and operation of Atlanta Police Department. So, here the words to be disambiguated are jury, administration, operation and police department. So, jury has 2 senses, administration has 3 senses, operation is ambiguous, very ambiguous, this has 8 senses, and police department has 1 sense. So, first we make a lattice of the nouns in the context and their senses and hypernyms. So, we can see here that administrative jury, the word jury has hypernym as committee, which again has hypernym as administrative unit. This jury has hypernym as body. Okay. So, we are talking about the 2 senses of the word jury. Then we find out other entities also in the context of the sentence. So, administration is related to body, operation is related to division, division again is related to administrative unit. After that, police department is taken, which has local department as hypernymy, which has government department as hypernymy, then department as hypernymy, then division, then administrative unit. Okay. So, this way we have built a conceptual subtree which is rooted at administrative unit, and another subtree has been built which is rooted as body. So, when these two trees are made, we are ready to compute the conceptual density of the resultant concept or the sub hierarchies, and the concept is with the highest CD is selected. So, this is the subtree which has highest conceptual density, and the senses will be picked up from here. So, a police department has a single sense, we do not have to worry about this. Administration has 3 senses, and we can pick up the sense from there, and jury has 2 senses, but this jury here has much more dense subtree compared to this jury here. So, this will be the winner sense. So, this is the main idea of the conceptual density based algorithm for sense disambiguation. Here the conceptual density is 0.256 and here the conceptual density is 0.062 as per the formula discussed before. Select the senses below the selected concept as the correct sense for the respective word. Okay. Now, the critique of this approach is that it resolves lexical ambiguity of nouns by finding a combination of senses that maximizes the total conceptual density among senses. The good part of this algorithm is that it does not require a tagged corpus, which is difficult to create. The bad part is that it fails to capture the strong clues provided by proper nouns in the context. So, this is a perennial problem for all overlap based approaches, and the accuracy of this approach is that it is 54% on the Brown corpus. The Brown corpus is the one which gives rise to SEMCOR, the sense smart corpus crafted out of the Brown corpus, and this has been a benchmark data for many WSD algorithms. So, proceeding further, we now take another algorithm which is word sense disambiguation using random walk algorithm, and this is based on the idea of page rank. The algorithm was proposed in 2007 by Sinha and Mihalcea. We take this example here of the sentence shown in the screen. The church bells no longer rung on Sundays. The church bells no longer rung on Sundays. Church has three senses. The first sense is one of the groups of Christians who have their own beliefs and forms of worship. The next sense is a place of public, especially Christian worship, and 3, a service conducted in a church. So, the church bells no longer rang on Sundays. Most likely it is the second sense which is applicable here. There is a bit of uncertainty, with respect to 2 and 3. It could it be the service sense, but most likely not. It is the place sense which is used here. Bell also has 3 senses: a hollow device made of metal that makes a ringing sound when struck, a push button at an outer door that gives a ringing or buzzing signal when pushed, the sound of a bell. So, the sense which is applicable here is the first sense, a hollow device. Ring also has 3 senses: make a ringing sound, ring or echo with sound, make bells ring, often for the purpose of musical edification. So, here the first sense is applicable, make a ringing sound. Sunday is the word, another content word. This is the first day of the week, observed as a day of rest and worship by most Christians. Sunday does not have too many senses, just one sense. So, it is monosemous. Now, our goal is to see out of these 3 into 3 into 1, which are 9 senses, which senses are applicable, that we know, but can the algorithm find it out. For church, it is the second sense. For bell, it is the first sense. Ring also, it is the first sense. Okay. So, here is the graph which gets built slowly. For each word in the sentence, bell, ring, church and Sunday, we erect the column of senses on the words. So, bell has 3 senses, S1, S2, S3. Ring has 3 senses, S1, S2, S3. Church has 3 senses, S1, S2, S3, and Sunday has a single sense. All right. So, add a vertex for each possible sense of each word in the context. Next, add weighted edges using definition based semantic similarity, the Lec method. So, we add weights from one word to the next word, okay, to the sense columns. So, here we build edges from S3 to S3 of the next word, S3 to S2 of the next word, S3 to S1 of the next word, similarly from S2 and from S1. So, we will have 3 into 3, 9 arcs growing from bell to bells senses to rings senses. So, the weightage of these edges would be equal to the overlap based similarity between the senses S3 and S2. So, we will take the synsets in S2 and take the gloss words and take the example words, and then see how much is the overlap between the corresponding entities in the other sense, and record that as the weightage of the arc. We do this for all the 9 arcs. In the step 3, we use the graph based ranking algorithm to find the score of each vertex, that is for each word sense. So, when this algorithm is run, then we find that at the convergence, these are the winner senses. So, S1 is the winner sense for bell, S3 is the winner sense for ring, make bells ring, often for the purpose of musical edification. Okay, we stand corrected here. We earlier said it is the first sense which was applicable. In this particular context, it is the third sense which is applicable. And for church, it is the second sense which is applicable in the context. Similarly, for Sunday, there is only one sense which is S1. So, these are the senses which have become winner after the page rank algorithm has been run. So, select the vertex which has the highest score. Now, this is the main idea, but what happens actually at the algorithm level. We look at the page rank idea and we make use of the Wikipedia description. Page rank was developed at Stanford University by Larry Page, hence the name page rank, and Sergey Brin as part of a research project about a new kind of search engine. The first paper about the project describing page rank and the initial prototype of the Google search engine was published in 1998. Shortly after, Page and Brin founded Google Incorporate, the company behind the Google search engine. And while just one of the many factors that determine the ranking of Google search results, PageRank continues to provide the basis for all of Google's web search tools. All right. So, this is a bit of historical remark on PageRank. What actually happens in the algorithm? PageRank is a probability distribution used to represent the likelihood that a person randomly clicking on links will arrive at any particular page. Okay. PageRank tries to capture this particular intuition. It is a probability distribution used to represent the likelihood that a person randomly clicking on links will arrive at any particular page. For illustration, let us assume a small universe of 4 web pages A, B, C and D. The initial approximation of page rank could be evenly divided between these 4 documents. Hence, each document would begin with an estimated page rank of 0.25. So, if pages B, C and D each only link to A, they would each confer 0.25 page rank to A. All page rank PR in this simplistic system would thus gather to A, because all links would be pointing to A. So, page rank of A is page rank of B plus page rank of C plus page rank of D, which comes out to be 0.75. Now, suppose that page B has a link to page C as well as to page A, while page D has links to all the 3 pages. So, the value of the link votes is divided among all the outbound links on a page. Since B has link to page C as well as to page A, we divide B's page rank into 2 parts and give 0.125 to A and 0.125 to C, dividing 0.25 into 2 equal parts. Similarly, since D links to both A and B and C, D's page rank is also divided into equal 3 parts and given to A. So, the modified formula for page rank of A, okay, compared to the last formula is this: page rank of A is equal to page rank of B divided by 2, page rank of C divided by 1 and page rank of D divided by 3. So, this is the modified formula. Earlier you remember there were no dividing factors. In general, page rank of a node U is equal to page rank of V divided by LV summing over all possible V's belonging to BU, where BU is the set of pages U is linked to and LV is the number of links from V. All right. So, this is the generalized formula and here is a example of its application to a specific situation. Now, what is the basic idea here? Let us get the intuition. First of all, we are saying that the page rank of a page linking to another page is transferred, and it is transferred wholly if the page from where page rank is coming links to only the receiving page, okay, only the receiving page. However, if the page rank conferring node links to other nodes also, then we have to divide this vote into n parts, where n is the number of links coming out from the page rank conferring page. What is the idea? And the idea is that suppose an important person praises another person. Okay. So, an important person, let us say X, praises another person Y. Okay. So, we would like to write it down, maybe when we write it, it will be clear. So, person X praises person Y. Okay. And this person is not only a person, it is an important person. So, since X has praised Y, Y's importance also goes up. Since X has praised Y, Y's importance also goes up. Okay. This is normal page rank transfer. However, if important person X praises Y, but he also praises P, praises Q, praises R, then isn't it true that because this person is praising so many people, okay, the importance of his praising goes down a bit. Okay. So, one would think that, well, person X is important, yes. If he selectively gives his praise to individuals, then there is some weightage in that praise. But if the person is owned to, okay, has the habit of praising anybody, then it is doubtful how much importance we would be giving to this praise. Okay. How seriously we should consider this praise becomes a debatable issue. So, that is why if you look at the writing here again, the person's praise goes to Y, P, Q, R, and it will be legitimate for us to say that the importance which person X transfers to these people can be looked upon as being divided amongst all of them. If it was only Y and not P, Q, R, then the whole importance of X is attributed to Y. But when there are more people and praise is given to all of them, then we are legitimate in thinking that the importance of X gets transferred to all of them equally. Okay. So, then we can say that transferred importance is equal to importance of X divided by 4, because there are 4 recipients, as you can see, Y, P, Q, R. So, this is the main idea behind page rank algorithm. The page rank is transferred from a person to another person, in this case a node to another node, and if there are many outgoing links from a node, we divide the page rank and send it to the receiving nodes. All right. So, coming to the slides now. The page rank theory holds that even an imaginary surfer who is randomly clicking on links will eventually stop clicking. That is true. the probability at any step that the person will continue is a damping factor D. So, that is a bit of adjustment to the PageRank algorithm for capturing the phenomenon of a person clicking on web pages. So, PageRank of a document U is PRV, sigma PRV by LV, which is the basic formula. This is multiplied by the damping factor D, and 1 minus D multiplies 1 minus D by N is the other factor. So, this of course, should move to here below. So, this is the modified formula for PageRank. Now, for Worsen disambiguation, how does PageRank apply? So, given a graph G V comma E, in V I is equal to predecessors of V I, out V I is the successor of V I. In a weighted graph, which is what our interest is in, our graph for the senses is a weighted graph. The worker randomly selects an outgoing edge with higher probability of selecting edges with higher weight. So, the weighted score of V I is equal to W j I, which is the weight between the node V I and the node V j, divided by W j k, which is for all the outgoing nodes or all the outwards edges to various nodes, and this summation is over all incoming nodes, okay, all nodes whose arcs are incoming on V I, okay, on incoming on V I. So, the picture is really that of what was shown before. So, we have these nodes which are the sense nodes on the words. For this particular, let us concentrate on this node. This node will be connected to the nodes in the next stage. So, its outgoing edges are from here to the next words nodes, sense nodes. The incoming links are these S3, S2, S1 to this particular S2. Okay. So, we have incoming links and we have outgoing links from S2, and we make use and we have the weightages on these arcs. So, now initially when the PageRank begins, we have some PageRank values randomly assigned to various nodes, and after that, by virtue of the PageRank algorithm, okay, the PageRank being transferred here, for example, is as per the weightage here, okay, weightage on this, and divided by the number of links, weightage of the links coming from S3. So, this is the PageRank transfer to S2, and from here again PageRank gets transferred to all these senses. So, these the PageRank here also get modified. So, this algorithm goes on running, and after some time there is convergence, and when the convergence happens, we get the winner senses. There are other link based algorithms which are used for ranking of web pages. HITS algorithm was invented by John Kleinberg, used by Teoma and now Ask.com, IBM Clever project, and then there is also something called the trust rank algorithm. These algorithms have not been tried for Worsen disambiguation. So, the critique of the PageRank algorithm, PageRank based algorithm is that it relies on random walks on graphs encoding label dependencies. The good part is that it does not require any tag data, a word net is sufficient. The weights on the edges capture the definition based semantic similarities, takes into account global data recursively drawn from the entire graph. And the bad is that in spite of its attractive properties and the attractive nature of the algorithm has poor accuracy. So, this is something which is worth investigating. The reasons are known of course, but as a student it will be useful to you to get an insight into the algorithm and understand why the algorithm has poor accuracy. So, this like the conceptual density idea, it also has about 54% accuracy on SEM-core corpus, which has a baseline accuracy of 37%. Okay. So, this would finish the knowledge based approach, and we can make some summarizing remarks here on the knowledge based approach to words and disambiguation. Words and disambiguation using selectional restrictions, where the arguments and the properties are considered. It has an accuracy of 44% on the Brown corpus. Lesk algorithm, which is overlap based, 50 to 60% on short samples of Pride and Prejudice and some news stories. Extended Lesk algorithm, it has an accuracy of 32% on lexical samples from Sense Eval 2. Well, the accuracy figure becomes lower because of higher topic drift. Words and disambiguation using conceptual density, it has an accuracy of 54% on the Brown corpus. Words and disambiguation using random walk algorithms, 54% accuracy on SEM-core corpus, which has a baseline accuracy of 37%. Walker's algorithm produces 50% accuracy when tested on 10 highly polysemous English words. Now, you see these accuracy figures are reported, but they cannot really be compared. Okay. The reason is that we are not using the same data for evaluation. If the same data was used for evaluation, then they were comparable, but these are some indicative figures which tell us what kind of accuracy one can hope for when one uses these algorithms. Okay. Proceeding further, we look at the drawbacks of WSD, which uses knowledge based approaches. The drawbacks of WSD using selection restrictions are they need exhaustive knowledge bases. All the properties of verbs and nouns have to be stored. Drawback of overlap based approach is that dictionary definitions are generally very small. Dictionary entries rarely take into account the distributional constraints of different word senses, for example, selectional preference, kinds of preposition, etc. Cigarette and ash never co-occur in the dictionary. They suffer from the problem of sparse match. Proper nouns are not present in the machine readable dictionary, hence these approaches fail to capture the strong clues provided by proper nouns. Now, we move on to supervised approaches, and we will just start it to be elaborated in the next lecture. In supervised approach, the whole idea is to have a sense marked corpus, okay, and we learn from the sense marked corpus, So, if you look at the slide, the first important approach to supervised approach is the naive Bayes algorithm. This is conducted through an argmax based computation. I will just put down the formula and make some initial remarks on this. The winner sense is obtained by computing the probability of the sense given the target words features. VW is a target words feature vector, and we do it for all possible senses, and the sense which has the best argmax score becomes the winner sense. The feature vector consists of part of speech, semantic and syntactic features, co-location vector, co-occurrence vector, etc. So, we will discuss this algorithm and see how sense marked corpus can be used for sense disambiguation.